All right, you guys, put your hands together for Andrew Ng. Come on, let him hear it.
Thank you. Thank you. We had a big AV scramble, so big thanks to Andrew Fong and also Sarah for helping out with this configuration. So as many of you know, in the past few years, there's been this rapid rise of a somewhat overhyped but also very exciting subfield of machine learning called deep learning. What I hope to do today is share with you some of the trends I'm seeing behind deep learning and how some of the trends I see in deep learning I think may affect your work in data science as well. I want to organize the material I want to present in 3 main application areas, images, speech, and then user behavior data. Let's start with images. Many years ago, maybe about a decade ago, when early work in computer vision tried to use machine learning algorithms to recognize coffee mugs, we would get results like this, right? Our software just found coffee mugs everywhere. And this was hard, and progress was slow, until several years ago, there came the rise of deep learning, which was loosely inspired by neurons in the brain and built neural networks like these in order to try to recognize objects better and solve a task better. And we were able to get very good coffee mug recognition and other things. So what is the neural network? I know many of you are already familiar with this, but whenever we draw a picture like this represents a relatively simple calculation to go from a set of pixel values to a classification values of a set of matrix multipliers and a few nonlinearities, right? And plus some simple rules for learning the matrices. And despite all the hype of deep learning, almost all the value today of deep learning is through supervised learning or learning from labeled data. All this talk about simulating the brain and so on, almost all the value today is driven by this one idea of learning X to Y mappings, in which you might have a lot of labeled data, a lot of pictures, some label, yes, it's a coffee mug, some label, no, it's not a coffee mug. And with a huge training set like this, you can learn very good coffee mug recognition systems. Now, everything I've said so far, almost everything I've said so far, has been around, maybe 20 years, maybe 20, 30 years. So I've said almost nothing that you wouldn't have heard others talk about, like literally 20 years ago. So why is deep learning taking off now? I often like to make an analogy between building deep learning systems to building space rockets. So what is a space rocket? A rocket ship is basically a huge engine together with a ton of fuel. And if you want to build a rocket, both of these need to be large. If you have a giant engine and a tiny amount of fuel, your rocket's not going to go very far. And if you have a tiny little engine but a ton of fuel, probably won't even lift off. And the only way to build a rocket is with a large engine and a lot of fuel. And the analogy is that the huge rocket engines we're now able to build are the very, very large neural networks we can now have. And the fuel is, thanks to the rise of the internet or mobile data, there's a huge amounts of data that we have access to. And it's not any type of data. Specifically, there's been large emphasis on labeled data, X-Y pairs. We have not just X, but also this X comma Y, where Y is the label that you're trying to get your neural network to output. And so at the risk of oversimplifying, I think that the rise of deep learning is all about scale. It's almost all about scale. And yes, in the last few years, in addition to scaling up the data, scaling up the algorithms, the computers, there has been a lot of some algorithmic innovation as well, but I think scale of data and of computation has been the platform that's enabled that also to make much more progress in the last several years. To give you a sense of the scale of progress of computation, many years ago, maybe 7 years ago, 8 years ago, most of us were running deep learning algorithms on a desktop computer, a single CPU. And we're training neural networks with about 1 million parameters. Then we started to use GPUs, a single GPUs, that allowed us to build much bigger neural networks with a lot more parameters. Starting 2011, a few groups, including a group that I led at Google, started to use cloud computing, many computers, to scale these up even further. And then a bit later after that, we realized that was the wrong technology and that we should instead be shifting to large numbers of GPUs. And so I guess first at Stanford and then at Baidu, we've been using HPC, supercomputer tactics or high performance computer tactics to build even more scalable deep learning algorithms. And I think this scale, the sheer scale of computation, together with the scale of data, has driven a lot of the progress across the entire field. So I showed you how we can recognize coffee mugs, right? And that's good. But there's such a gulf between recognizing coffee mugs and what we would like computers to be able to do. So can the computer possibly ever understand these images? If I were to ask you to write captions for these pictures, you might write, something like this, right? Yellow bus driving on a road, green grass, and so on. Picture on the right, room in the apartment, get some afternoon sun. And your ability to write captions like these shows that you have a much deeper understanding of what's going on in these images than saying, oh, there's a bus or there's a sofa, right? There's this huge gulf of understanding between object recognition and what a human can write, like captions like these. Well, I have a surprise for you. These captions weren't written by a human, they're written by a computer. And the way it was written was with a deep learning algorithm that learns one of these X to Y mappings. And so a lot of recent progress is that Y can be increasingly complex in structure, even entire sentences. So simplifying the picture a little bit, we use a neural network to input a picture and output a caption. I was quite proud that Baidu was the first organization working with UCLA to figure out and publish and announce this architecture. And actually a lot of other groups have been building on our work on this since then. And we can do even better, not just X to Y being image and caption. It can be image, comma, a question, and then an answer. And with this type of neural network, we can input a picture and ask the question, like, what's the color of the bus? We did this work in Chinese Mandarin, but I'm just going to present the English translations. We can ask, what's the color of the bus? And given enough pairs of X, comma, Y of label training data, we find that our neural networks, with some additional details, are able to learn, to input a question, comma, input an image, comma, a question, and in many cases, output a text answer. So computer vision is really taking off. What is this good for? It turns out that computer vision monetizes really well. We actually bring in significant revenue at Baidu using computer vision. I don't want to talk about that now. You can actually ask me about it. We're not that secretive about most of what we do. But what I wanted to do today is tell you about an application that I find inspiring, that we've been working on in Baidu research. This is the first time I'm talking about or showing this in the United States. This is an application called DoLight. I should say this is a research project, research prototype called DoLight. This is the first time anyone in the United States is seeing one of these live. And it's a little built-in wearable camera that you wear above your ear, so the camera can see what you see. And we have been building functionality to use it to help enable blind people to understand the environment around them better. So let's see. Could one of you volunteer, stand up? So if I were blind and I were to see, actually, all right, this gentleman in front of me, and normally I wear this, wow, all right, it's kind of dark. Let's see if this works. I see, cool, thank you. So what I just did was I took a picture with this. Normally I wear it over my ear and bend down and so on. And this picture was transmitted to our servers in Beijing and run through our captioning software. What happens then is that it tries to recognize what's in the picture, and if it's confident, it returns the answer right away. If it's not confident, there are human backups. But so, oh, I see. Sorry, you can't see this, can you? All right. Let's see if this works. We couldn't figure out all of the AVs, so this is a guerrilla. We're all technical people, right? Can you guys see that? All right. So you can not sure you can see the Chinese caption, but the Chinese caption says 短发帅气男人, which means a short-haired, handsome man. Pretty accurate, right? So that's just one of the applications. I'll quickly show you our vision for this. All right, there's and the life of the blind is very different than you and my lives. If you were blind, you wouldn't be watching this video. And who else needs sight more than the blind? So with the mobile version of this, without the built-in camera, you can look at the little carton and tell you, is this juice or is this fresh milk? Right? You can't tell different cartons apart by touch. And there's also a speaker, so it speaks into the ear. when you're lost, this actually connects you to a human person if necessary. So it's telling him that the light is green and safe to cross. Built-in face recognition, so it can recognize individuals whose faces you have. Many denominations in China are the same size, so it's hard to tell by touch and tell you what denomination money is. Let me tell you how you're doing. Right. Thank you. Thank you. So that's one of the projects of computer vision that inspires me, because who needs eyes more than the blind? Let's talk a little bit about the second area I'm excited about, speech recognition. Traditionally, speech recognition has been done with incredibly complicated software pipelines. We input the audio, extract features, figure out phonemes, toss in a language model, you figure out a transcript. It's really complex pipelines. As deep learning people, we said, let's take the whole thing and just blow it away and replace it with a deep learning algorithm. So that's our rocket engine. Huge neural networks to do this. And then what's a rocket fuel? In academia, people train on maybe 2,000 hours of training data. We said we need more data than that. We need more rocket fuel than that. So we started off with 100,000 hours of data. And so with this formula, and additional details we talk about in the papers, but rocket engine, rocket fuel make both really big. Over the past several months, we've been able to drive down speech recognition errors significantly. This is our results on Mandarin speech recognition, and then since February, I guess, working on this several months using scalable deep learning, we're able to drive errors down below the previous best system that we had within Baidu. So we're building production servers and working to roll this out to users now. And I think speech is one of the areas I'm very excited about. Most people don't understand the difference between 95 and 99% accurate speech. Speech recognition today, depending on how clearly you speak, whether you have an accent, maybe it's 95% accurate. And that means it's painful to use. It gets one word in 20 wrong, and you have to go in and correct it. 99% is game-changing. I think the whole world is moving to mobile devices, and all of us spend so much time typing on these tiny little keyboards. If we could make speech just work and have it just be reliable, you use it all the time and you won't even think about it. So we've made a lot of progress. We still have some steps ahead of us, but this is one of the technologies that I think could transform everything, could transform the way a lot of us interact with technology. And beyond cell phones, I think, I hope that several years from now, we'll be talking to our cars, talking to home appliances, and talking to wearable devices. For many applications, not all applications, but for many applications, I think speech is a very natural interface and will make it much easier, much more convenient for us to interact with technology. So the last vertical, and let's talk about this very quickly, is user behavior. We find that by building an internal platform to let engineers run very scalable deep learning experiments, this has empowered many engineers in Baidu to take a lot of the applications where we have labeled data, X, Y, to input something and output, make a prediction. And so ranging from web search or advertising. So I think that we use deep learning to predict CTR click-through rates, right? How likely a user is to click on an ad. This is a very direct and very significant impact on our revenue. It's direct impact on advertising. To data center management, with a lot of data on machines going down, and so we can use that to predict. To computer security, where X is the status of something and Y is this a security threat or not. And so today we do all of these things and many, many more using deep learning, because we have supercomputers or these very scalable systems and huge labeled data sets. So in addition to labeled data, there is a lot of good basic research on unsupervised learning, reinforcement learning, on many elements, other elements of deep learning. But almost all the value today, almost all the economic value today so far is created by supervised learning, and I think is almost all about scale. And I want to just give you one final lens to think about the rise of deep learning. And this may relate to some of the work you do in data science as well, which is that for the earlier generations of learning algorithms, support vector machines, decision trees, boosting, most flavors. For most flavors of the older generations of learning algorithms, even as you fed it more data, its performance would plateau. It's difficult to get them to keep improving with the availability of more data. And deep learning, as far as I can tell, is the first class of algorithms that is scalable. So we could actually implement these on our supercomputers to build really big neural networks. And when you build a big enough neural network, its performance just keeps getting better as you feed it more data. So for companies with a lot of data, our deep learning algorithms are outperforming the earlier generations of algorithms. And one question I have for you that I actually don't know the answer to is when you look across your portfolio of data science techniques, how do they scale with the amount of data? I don't actually feel like I know the answer to that. I'd love to explore the answer to that question with many of you. But I think that algorithms that scale more like the blue line are more likely to be future-proof, even as all of us get more and more data. I want to finish with this one more demo and maybe one gift to all of you for Halloween. Talk about building supercomputers to train really, really large neural networks. That raises another problem of scale, which is the whole world is moving to mobile. Baidu is a mobile-first company. Most of our revenue comes from mobile. After we build something on a supercomputer, how do you deploy these huge neural networks on your cell phone, right? It's like the bigger scale and the smaller scale. So I want to give you an example. One of the applications we built requires recognizing a lot of key points on the face. And initially, we had over 100 megabyte binary to do this. And you can't get users. You don't want to ask users to download a 153 megabyte binary, right? This is too slow. And with a lot of work, we were able to take a very large model and compress it to something much smaller. And this is key to allowing us to build and ship an application called FaceU. For those of you who have an iPhone, I want you to see this yourself. If you have an iPhone, take out your phone and search for FaceU on the App Store and install. And I want you to be able to see what this does for yourself in real time. So take out your iPhone, with apologies to the Android users, and search for FaceU so you can see this for yourself. And while you do that, I'm going to try to plug in my phone so we can do a live demo as well. Right, so search for FaceU on the Apple, on the iPhone App Store. And I'll try to swap this in while you do that. So we've done a lot of work building face understanding algorithms, and then about a month ago, one of our engineers said, "Hey, I want to build this other thing." Okay, excellent. And so this is the FaceU app. So it detects my face in real time, and I could have given the whole talk like this, right? And I don't know, some fun ones, right? And it's actually pretty terrifying how, well, notice how when I blink, right, and when I talk, it's just, so I told my wife, Carol, that I didn't have a Halloween costume this year, but that FaceU would be my costume. And she said, that's kind of lame. But, oh, sorry, I flipped the camera. But the other thing I did was, this is actually my wife. So you can also take pictures of your friends and put them in here, and you can overlay their faces on yours, which is another type of Halloween costume. All right. So thank you. Thank you. So we just announced this yesterday. So you're among the first to see it. Hope you have fun with it on Halloween tomorrow. Just two more slides, really. AI deep learning has been taking off over the past several years, and this is transforming the way we can recognize, process images, process speech, and process user behavior data. And I just want to close with one last thought, which is that I think when I look at the state of deep learning, when I look at the state of data science, I feel like all of us in this room, right? All of us in this room, we have superpowers. I mean, with AI and with deep learning, we can help computers understand images better. We can even, with deep learning, we can help blind people see. I mean, what could be cooler than that? Our systems are starting to understand language better, just the beginnings, and we're having software that can understand user behavior much better. And I am very excited about all the progress that all of us have made already in the past several years, but even more excited about the progress ahead of us in the next several years. So I hope that all of us, all of you in this room, after today will go home and use these superpowers that we have to create the best possible things for humanity. Thank you.
Wow. Does anybody feel bad about themselves after that presentation?